Today we'll talk a little bit about what order of growth means, give you some more tricks in finding it. So we'll talk about something called the limit test, which is a good way of characterizing big O, big theta, big omega for algorithms. And then we'll go through some basic summation notation. So some of this will be a recap, some of this will be kind of new. But what's the big picture? So our big picture is that we want to analyze algorithms in terms of how sensitive their running time is to changes in their input size. So a big picture looks something like this. When we look at an algorithm, first we want to pick some important operation in that algorithm that runs kind of the most, right? Is executed the largest number of times. So we want to pick a basic operation. So then we want to determine what we'll call T of n, which is the number of times that basic operation executes. So determine, and this will be like a function, like we actually want to find the function that tells us this. So determine T of n, where T is the number of executions, and n is the input size. And then third, we want to determine the order of growth of T of n. So last time we talked about big O, big omega, and big theta. So what this means is we literally want to determine big theta for T of n. So then we want to find T of n is big theta of what? Right. So we want to plug something into that question mark that makes this true. All right, once we've found that, we have some really important information. So I find that it's often handy to kind of remind ourselves what big theta means, right? So if I say an algorithm has a running time, that's big theta of n squared, what is that telling us? So here's a quick chart that I like to have in mind, which gives you some sense of what these things actually mean. So here's my cheat sheet reference chart for this sort of stuff. So let's put the order of growth over here. So order of growth. And then what I'm going to write is the result of doubling the input size for large inputs over on the right. So this is doubling input size. Okay, so suppose T of n is a super fast, it represents a super fast algorithm. So suppose T of n is big theta of 1. Right, so this means that the running time of the algorithm does not substantially depend on the size of the input. And so here, what do we have? Well, we have this fact that T of 2n just equals T of n. Right? So there's no dependence on input size, essentially, right? Essentially for large inputs, if we have an algorithm that runs in constant time. Okay, that's what big theta of 1 is called, constant time. All right, so I'm going to write this kind of hierarchy where our algorithms get slower and slower as we go. So now what if T of n is big theta of log n? Well, log n is also extremely fast, right? If an algorithm runs in log time, that means it probably doesn't have to process the entire input. Somehow it can get away with only processing some of the input. And so what is T of 2n? Well, T of 2n is essentially T of n plus 1, right? It's just a constant amount slower than T of n. So T of n plus 1. Right? Just a constant amount slower. Okay? So now what if we go up to another complexity class? What if we go up to T of n is big theta of n? What does this mean? Well, so this means that T of 2n is just exactly double, right? Or approximately double T of n. 2 times T of n. Right? And so this is like in the examples we've looked at with the triangles and the grids and things like that, this is like the way a line grows. This is the growth of a line. Right? So now, doubling the input size doesn't have a huge impact. And no matter how big the input is, it doesn't really do much more than just doubling the running time. All right, so let's keep going up. So T of n is big theta of n log n. So this is a combination of the above two complexity classes. And now things are going to start to get a bit slower, but not by too much, right? So this looks something like t of 2n is double t of n plus some linear amount. So one way we could write that is like this. We could write 2 times t of n plus n, right? So yeah, we have a doubling effect, and then we add on this linear amount, right? But it's not going to grow by substantially more than just doubling the size. But it doesn't scale quite as well as the big theta of n. So if I say t of n now is n squared, big theta of n squared, what is this telling me? Well, now this is the triangle or the grid, right? This is when we start to get a quadrupling of the running time. So here t of 2n equals 4 times t of n. And really for all of these, I should put a wiggle, right? So this is not equals in a strict sense. This is approximately equals in an asymptotic sense, right? If I have very large inputs, this is about how this algorithm will behave. Okay, so now I could say, okay, what about t of n equals, or is a member of big theta of n to the k, where k is some power now. Well, now we're getting into some worse scaling. It's actually not egregiously bad yet, but this is going to look something like 2 to the k t of n, right? And you can actually plug in 2 for k if you like, and you'll just recover the same n squared quadratic scaling that we saw before. All right, so all of these are polynomial. All right, so we call these all oh, this is not quite working. Right. We call all these polynomial time algorithms, right? Everything that is n to the k and faster, we think of as a polynomial time algorithm, and that's sort of the lingo for it. So there's this important line right here where polynomial time algorithms tend to be algorithms that scale well, right? Sort of by definition, they're algorithms that scale well. But then there's this line where once you cross over the line, you're in an exponential type of a world, and things start to get much, much slower, and they scale very poorly. And so we'll talk about the kind of the fundamentals of this line later in the course, but for now, just know that the crossover between polynomial and exponential is a bad one. You really, really want to be above this line. So t of n, say t of n is big theta of 2 to the n, right? So now this is an exponential characteristic. So now what happens if I double the input size? Well, I don't just multiply a factor on anymore. Now I square the running time, right? So this is approximately equal to t of n squared, right? And so this now is starting to get quite bad because now the larger my input, the larger my running time, but that means that I'm multiplying on that extra larger running time again when I double the input. Right? So things get quite bad, and then things get kind of horrifically bad after this. So t of n, could be n factorial. We'll talk about factorial in a minute, but it could be n factorial, and that's really a disaster, and it's so bad that we don't even have a good mathematical expression for it. So I'll just write so bad here. Right? Things get bad that even the mathematicians have a hard time writing down closed forms for it. So this is the basic hierarchy. Always keep this in mind, keep this ranking in mind. And I think one of the most important reasons to have this in mind is to actually have a sense in your brain about what these things look like on this side.